This video provides an introduction to the analysis of transportation projects using RETScreen Expert. The RETScreen Clean Energy Management software can evaluate various types of transportation projects. It can be used to investigate the viability of energy efficiency improvements in a wide variety of on-road vehicles, off-road vehicles, aircraft, marine, train, and other modes of transportation. It can also track the fuel consumption and usage of existing transportation systems. A single vehicle or an entire fleet can be analyzed. Fleet managers can employ this to track fuel consumption, costs, and GHG emissions. There are organizations using this to track emissions from employee travel and commuting, letting RETScreen be a key part in tracking Scope 1, 2, and 3 emissions. Let's start by looking at transportation feasibility analysis. There are a number of ways to launch a feasibility analysis of a transportation project in RETScreen Expert, including several case studies and templates, many archetypes in the Virtual Energy Analyzer, and even this shortcut button on the home page, which quickly loads an example case study. I'll use the Virtual Energy Analyzer to load one of the many built-in transportation archetypes, letting me start a pre-feasibility or feasibility analysis quickly. The Virtual Energy Analyzer is a way to configure RETScreen with values relevant to a particular project scenario, referred to as an archetype. If the archetype is similar to the project you want to analyze, the values RETScreen selects for inputs to the analysis may be appropriate for your project and only need minor refinements. As usual in RETScreen, the archetypes compare a base case, typically corresponding to a conventional or the current status quo situation, often wasteful of energy, with a proposed case, typically an approach that reduces the consumption of conventional fuels. The savings and costs of the proposed case are calculated in comparison to the base case. The Virtual Energy Analyzer can be launched from the home page using the button found under Getting Started Options. I need to select the archetype and the location of the project. For transportation projects, select Transportation for facility type and then choose from the type, which includes a wide range of archetypes for aircraft, marine transportation, multiple modes, off-road vehicles, on-road vehicles, other modes of transportation, and trains. The archetypes are arranged under 3 headings: those for approaches that minimize the end-use need for energy, those for measures that maximize efficiency, and those for projects that optimize the way energy is supplied. Before examining an archetype in detail, I'll enumerate the transportation archetypes available at the time this video is being recorded. For aircraft, there are archetypes that involve an analysis of a way to minimize usage based on how the aircraft is operated, such as converting from step descent to continuous descent, shutting down one or more engines while taxiing, and continuous optimization of speed. Archetypes for maximizing efficiency by changing something on the aircraft itself cover replacement of existing engines with newer, more efficient ones, components to reduce aerodynamic drag, use of lighter containers for freight air travel, replacement of an older airplane with a newer, more efficient model. Under Optimized Supply, there are archetypes for using grid electricity, rather than onboard generators, to power air conditioning for a plane at the airport gate, and for using biofuel blends. For marine transportation, the archetypes show many ways to maximize efficiency, including air lubrication, hull and propeller optimization, and others listed here. Under Optimized Supply, there are archetypes for using shoreside power instead of onboard diesel generators while a ship is berthed, using wind to aid propulsion of a cargo ship, fuel switching, installing PV panels on available deck area on bulk or tanker ships, and recovering waste heat from engine exhaust. Multiple modes cover situations where there are several ways to move things or people around. For example, 2 archetypes analyze switching employee travel for short distances from airplane to train, with one archetype for large organizations and another for small ones. Another archetype analyzes using train instead of truck for freight transportation. Off-road vehicles can include recreational and work vehicles used in rugged or hard-to-access terrain, such as this archetype analyzing the feasibility of switching from fossil fuel power to electricity for snowmobiles and utility terrain vehicles. There are many opportunities to dramatically reduce fuel consumption for on-road vehicles. These include minimizing usage, where one finds archetypes for automatically starting and stopping the engine during idling, carpooling, and use of route optimization software for a fleet of vehicles making deliveries. To maximize on-road vehicle efficiency, archetypes include installation of aerodynamic drag reducing fittings, automatic tire inflation systems to reduce rolling resistance, driver training programs, telematic systems for centralized fleet management, preventative maintenance programs, switching to hybrid power systems that switch off the engine and use batteries instead, hybrid diesel battery power for fleets, and optimization of vehicles selected for a small fleet. Optimizing vehicle use includes switching from individual cars to urban buses, switching a fleet of internal combustion engine vehicles to a mix of electric, hybrid, and more efficient new internal combustion engines, switching a fleet of buses from diesel to electric power, and switching a fleet of buses or trucks from diesel to biogas. Other transportation can include tractors, forklifts, generators, lawnmowers, ice resurfacers, and other engines that consume fuel. The two archetypes shown here, one for the reduction in fuel used by tractors through no-till farming methods, and a second for switching a fleet of forklifts from propane to electric power, are only two examples. For trains, there are archetypes for systems that reduce idling of engines, intelligent telemetry systems, and optimizing train speed based on train length, weight, and track grades. RETScreen also provides archetypes for electronically controlled pneumatic braking, which allow for more rail cars to be added to the train, using multiple smaller diesel engines rather than a single large engine, allowing for some engines to be shut off during periods of low load, replacement of the existing main diesel engine in an old locomotive with a more efficient one, a hybrid diesel-electric engine or an electric-only engine, and application of a friction-reducing treatment to the top of the rails. For this video, suppose the school administration operating in the town of Hope, British Columbia, Canada, wants to explore the feasibility of switching a fleet of 10 diesel school buses to electric buses. I'll use this archetype here, under On-Road Vehicle, to help. Clicking on the Calculate button fills the analysis with values appropriate to this archetype. The location worksheet shows the climate data for the location. The facility worksheet indicates how this analysis is configured and provides some benchmark information summarizing the project. We can confirm that this is a feasibility analysis because the feasibility button is highlighted. The menu items that have been selected for facility type, and description come directly from the Virtual Energy Analyzer. We could add information about this analysis in the remaining facility information inputs and change the image if we wished. At the bottom of the worksheet, there is benchmark information. The archetype has assumed that the school buses in the fleet will travel a combined 220,000 kilometers per year. From the benchmark database, it has selected a benchmark in equivalent energy units of 3.8 kilowatt hours per kilometer for on-road school buses with an internal combustion engine. Although the units of kilowatt hours are often associated with electrical energy, here the energy in diesel fuel has been expressed in kilowatt hours, allowing for direct comparisons between diesel consumption in the base case and electricity consumption in the proposed case. The values in this lower section here come directly from the energy worksheet. When you use an archetype, RETScreen will automatically extract this information and copy it here. I'll show where these figures come from in a few minutes. Turning to the energy worksheet, we should start by reading the notes at the bottom of the Include Measure page. These include the principal assumptions for the archetype. This archetype has replacements for a fleet of 10 school buses at the end of their normal life. The base case has internal combustion engines, and in the proposed case, the buses will have electric drive and batteries lasting around 15 years. The school district will also need to install 10 overnight charging stations. The manner in which the archetype has estimated the incremental initial costs and operation and maintenance, or O&M savings, for the proposed case versus the base case are also shown. The electric buses cost about $250,000 more per bus than the internal combustion engine buses, and to this must be added the $180,000 combined cost of 10 charging stations. The electric buses have lower O&M costs, however, leading to an annual savings of about $4,400 per bus. These O&M savings do not take into account fuel savings, which are calculated elsewhere. On the Electricity and Fuels page, I can adjust the cost of diesel and electricity. Let's suppose the cost of diesel is $1.50 per liter. On the school bus fleet page, I can see the energy-related inputs specific to the base case and the proposed case. In both cases, the archetype assumes each bus in a fleet of 10 buses travels 22,000 kilometers per year. In the base case, the fuel is diesel, costing $1.50 per liter, and each vehicle consumes 43 liters of diesel per 100 kilometers traveled. This efficiency figure might be found on a specification sheet for the bus or from records kept for existing buses. But if that information were not readily available, a first estimate could be found in RETScreen's help. It contains a table for the typical average efficiency values for on-road internal combustion engine vehicles. It shows that for school buses operating on diesel fuel, the fuel efficiency can range between 20 and 60 liters per 100 kilometers. The value used in the archetype, 43 liters per 100 kilometers, is roughly in the middle of that range. Based on this fuel efficiency, the distance traveled per year per bus, the number of buses, and the cost of diesel, RETScreen finds an annual fuel consumption in the base case of 94,600 liters, which contains a little over 1 million kilowatt hours of energy, costing $141,900 per year. In the proposed case, from a wide range of potential vehicle types, an electric-only vehicle has been selected for the archetype. As in the base case, there are 10 buses, each traveling 22,000 kilometers annually. In contrast to the base case, however, here the buses consume only electricity at an average cost of 10 cents per kilowatt hour. The efficiency of the bus is 88 kilowatt hours per 100 kilometers. Note that the two unit switches allow the efficiency to be specified in liters for diesel and kilowatt hours for electricity. Once again, help contains a table that can provide a first estimate of the bus's efficiency. The table's value for the efficiency of an average school bus matches the value used in the archetype. The total annual consumption for the 10 vehicles is 193,600 kilowatt hours of electricity, which costs $19,360 per year. This is significantly less than in the base case, both in terms of total annual fuel consumption and annual fuel costs. At the bottom of the page, the archetype has specified the incremental initial costs and O&M savings. The estimation of these values was previously explained in the notes at the bottom of the Include Measure table. The Include Measure table summarizes the key outputs for the options under consideration. For this school bus fleet, the electric buses of the proposed case annually consume 813,000 kilowatt hours less fuel energy than the diesel buses of the base case, resulting in fuel cost savings of $123,000 per year. To this can be added incremental O&M savings of $44,000 per year. The proposed case costs $2.7 million more initially, however, resulting in a simple payback period of 16 years for the proposed case versus the base case. The comparison page summarizes the consumption of diesel and electricity in the base case and the proposed case and indicates the savings for each. The negative savings for electricity results from electricity being consumed to charge the buses in the proposed case, but not being consumed by the diesel buses. The savings section compares the total fuel consumption in units of kilowatt hours for the base case and the proposed case. The plan column shows where the figures from the previously viewed benchmark section of the facility worksheet come from, and the variance column expresses the relative difference between the fuel consumption and savings according to the feasibility study and according to the benchmark section. Remember that when loading an archetype, these values are automatically copied to the base case and proposed case sections in the benchmark page, so the variance is 0. The Update Plan button lets you copy these values manually. The benchmark table, shown at the bottom of the comparison page, has the total distance traveled by the fleet, which can be synced with the value on the benchmark section of the facility page using the Copy from Facility button. Then the base case and proposed case specific consumption in kilowatt hours per kilometer is compared with the benchmark value. The variance is the relative difference between the two. The costs from the energy worksheet have been carried over to a level 1 analysis on the cost worksheet. On the emission worksheet, A Level 1 analysis provides estimates of the greenhouse gas emissions in tons of CO2 equivalent per year from the school bus diesel consumption in the base case and electricity consumption in the proposed case. The emissions for electricity are calculated based on the GHG emissions factor for BC. Emissions are 98.5% lower in the proposed case than the base case due to British Columbia's generating most of its power with low emissions hydro projects and due to the higher efficiency of battery electric buses. On the finance worksheet, the project life of 15 years concords with the 15-year battery lifetime mentioned in the note at the bottom of the include measure table. It is assumed that 70% of the initial costs will be paid for with a loan. The net present value is negative, meaning the pre-tax internal rate of return on equity is lower than the minimum acceptable rate of return, as specified by a discount rate of 9%. The cumulative cash flow graph shows that it would take nearly the entire project lifetime for the initial equity investment in the project to be paid back by the project. That is, it has an equity payback just short of the 15-year lifetime. The risk worksheet can help investigate what would need to change in this archetype in order for it to be financially attractive. The risk worksheet contains a sensitivity analysis, which shows the value of one key financial output, such as the net present value, for different combinations of key input variables. Orange-red table entries indicate combinations that result in a financial output value below the specified threshold. The risk analysis allows for simultaneous variation in a wide range of input variables. While the energy, cost, emissions, and finance page provide estimates of key variables, those estimates have uncertainty. In the risk analysis, for each of these key variables we specify a range or interval that we expect will contain the true value of the variable. The risk analysis allows the key variables to randomly vary within these ranges and sees what the overall impact on the selected financial output would be. Here, that is the net present value. The most impactful key input variable, that is, the one with the longest bar in the impact graph, is the initial costs. The second most important key input is the fuel cost in the base case. We should focus on getting good estimates for these variables because they are so critical. In contrast, we do not need to worry much about minor inaccuracies in the debt interest rate, electricity cost, or debt term. The distribution graph shows a histogram of the net present value or other financial output based on random variation within the specified ranges for key input variables. The tails of the histogram can be clipped to exclude a percentage of the values that are most extreme. This percentage is specified by the level of risk. In addition to this type of feasibility analysis, RETScreen can analyze the performance of existing fleets or projects. There is an example portfolio showing this, which I will introduce here and explore in more depth in a separate video. Fleet managers can use RETScreen to track fuel consumption and usage data as well. I have here fuel consumption and mileage data for a fleet of different vehicles. Each transportation type and fuel type can have its own table, and the data can be imported directly into RETScreen. The mileage or usage can also be tracked for all transportation types. Tables summarizing the total fuel, cost, and total GHG emissions can be created, which automatically update whenever new data is available. Finally, there are various graphs and charts showing progress over time. These can be included in reports and custom dashboards, and most importantly, can be included with the rest of an organization's energy and emissions tracking as part of a portfolio. I'll show how to do this in another video. As shown previously, the school bus fleet is but one transportation archetype within RETScreen. In subsequent videos, we'll look at different transportation archetypes, a built-in example analysis within RETScreen, and a built-in portfolio including performance analysis of measured fuel consumption for a small fleet of vehicles.